Hi, I'm Jorge Gonzalez. I'm going to talk about some of my experiments with Explorer games using the SP1 library for the ZX Spectrum computer. Um, I am a Z88 DK contributor, mainly on SP1 and also the Arcos Tracker sound integration, and I'm also present in Z88DK and Spectrum Computing forums, plus Z88DK Telegram channel. I'm also a huge fan of Mohon Twins. Their Churrera engine made me start my own adventure engine, which is called Rage One, and you may have heard about it, and you can just search for it. First, I'm going to speak a bit about how SP1 library works. Um, SP1 is a library which is used to manage a sprite and a background layer in your game, and they are managed in an integrated way. Uh, I'm not going to talk about the sprite layer because it is not relevant for these experiments. In fact, we are going to use the sprite layer in a very trivial way just to move something over the screen. But the interesting part is the background layer and how it is managed. SP1 uses the equivalent UDG definitions, 8 bytes, for all the cells in the screen to draw the screen when it needs to. Um, it keeps a global tile map with a position for each of the screen cells, and it holds a 16-bit identifier for each of the cells. The 16-bit identifier may be a number from 0 to 200 and 255, in which case this number will be used as an index into another table that SP1 also maintains, which is the default type table. And in that table, we will find the pointer to the UDG associated to that ID, which is less than 256. In the case of the identifier being greater than 255, it is used the 16-bit number will be used as a pointer, and this pointer will be assumed to point directly to the 8-byte UDG definition for that cell. So this is what will be used to draw it. Um, this second mode is useful when you have more than 200 tiles in your game, or you want to be very flexible when defining tiles. The background tile definitions are static normally, and they are just initialized at the beginning of the game. And well, as your game switches screens, of course, the background changes and new screens are drawn, but the definition of the tiles themselves does not change. But what would happen if we could change them uh, sometimes during the game? Maybe we could get something like animated tiles. Uh, in fact, this can be done. I have already done for my Rage 1 library. And but one step further, we could go and say, how about changing all the background frame, all the background tiles on every frame? Could it be done? Now, some scrolling basics. Um, we're going to use the technique of a virtual screen for scrolling because, well, we could do it directly on the screen, but this would complicate the scrolling routines quite a bit because the screen layout of the Spectrum is a bit awkward. And on the other hand, the virtual screen has the advantage that we can manage the layout in whatever way we like, and we just need to have a very fast transfer routine for just bleeding the whole virtual screen to the real screen whenever we need. This technique is a bit less performant than scrolling directly, but on the other hand, is much more convenient because you don't need to raise the beam or to do other techniques that are quite advanced, and is also more predictable. So and also this way of handling the virtual screen is going to be very useful for us, as we will see in the next slide. Now, what we are going to do for SP1 scrolling is to lay out the virtual screen in a specific way so that we can use it easily to define the background tiles in the SP1 background tile map. So for this, we need to do it in an SP1 compatible way. So this way is that we are going to do it by character cells in 8-byte UDGs, like is the standard SP1 file format, and we are going to organize the cell in column major form, which is top to down on a single column, then left to right for the remaining columns. This will allow us to scroll a complete column, real fast in 1 pixel increments, or even faster if we want. And then we will make the cells in the global SP1 tile map point to the respective positions in the virtual screen. Uh, and then the main point is that we are going to modify our virtual screen in real time every frame and make SP1 update the screen. We are just going to do our scrolling in the virtual screen, and then we are going to tell SP1 to update the real screen on every cycle. If we do it this way, we have the two SP1 layers, the background and the sprite layer, all managed by SP1. And we can do whatever we want with the background since it's a virtual frame buffer, and in fact we are scrolling it. And SP1 will take care of updating it when needed. And as a bonus, it will include the sprites over it if we did put some sprites. So this is great. So for the examples of this video, I have set up a GitHub repository. The URL is the one that you can see on the screen, and it is organized in an easy way so that you can search for any of the examples that we are going to use later. There is a documentation directory where you can find the source for the most of the articles about this that I have published in the forums. And also there's an source directory which has a directory for each of the examples, and also some other tests that I have been doing, uh, not related to SP1 but related to scrolling. Um, you are very welcome to clone the repository and explore it and do whatever you want with it, and show any comments. So with the examples. My first example is a proof of concept to see if SP1 updating a reasonably large area on every scroll cycle makes a good frame rate, or it is too slow. Uh, Initially, our work area would be 16 by 16 character cells, and we need to introduce the concept of SP1 invalidation. What is it? It is the procedure of telling the engine that some of the cells on the screen are dirty and need to be redrawn on the next refresh. So there is a periodic call to function SP1 update now, which redraws all the cells that have been invalidated since the last call to SP1 update now. And as a proof of concept, we are going to invalidate the full scroll area every time we need to redraw it. The proof of concept is the test number 0, which can be found in the SP1-baseline directory. And as I said, we want to measure raw SP1 update performance when invalidating the full area. We are going to see the proof of concept in action here. And as we can see, there is quite a good frame rate, 22 frames per second. The layout is really simple. All the tiles of the screen are set to point to the same tile definition, which is being scrolled down one line on every cycle. So we're just measuring how fast SP1 is capable of updating the whole scroll area. As I said, 22 frames per second seems quite a good number. So this allowed me to continue to the next tests. So my first initial implementation, which is the next test, is test 1, which can be found in directory sp1-random tiles. It is the first test that implements a full scroll loop with something interesting happening on the scroll area. First, we have already arranged the virtual screen in columnar order, as can be seen in the green lines there. Virtual screen cells are stored by columns top down, and then going left to right for each of the columns. And the SP1 background tile map, the cells are set to point to the corresponding definitions in the virtual screen. There is also an external scrolling loop which handles repeated scrolling, and also this important function paints an additional row which is invisible and is at the top of the virtual screen buffer. This is the row that is being redrawn when new content needs to be scrolled into view by in the lower part of the scroll area, which is the visible one. There are also different scrolling functions that I have explored for different algorithms. The first one used an LDDR instruction. The second one used an unrolled LDDR loop in assembler. And the third one was using stack-based transfer, and they are all available in the source code. You can check them out. But spoiler: the fastest one is the LDDR based. And an important thing about this is that when we are scrolling a column, we are scrolling the full column, and then we are scrolling all the columns in turn from left to right. This means that initially there's no optimization about what is going to be scrolled and what is not. All the screen is going to be scrolled. For this demo, we can see it in action here, and we can see there's a smooth scrolling going on. The red and black colors are just the attributes to see the cells, but you will not see them in the next examples. And as we can see, there are 18 frames per second, between 17 and 18. So this seems good again. So we continue. So my next test is test number 2, which is called SP1-sprites in the repo. As you can imagine, this time we are going to add the sprites moving all around the scroll area together with the scrolling. Um, in this example, we are still scrolling the whole column for the backgrounds and invalidating whole columns. So it's the whole area being redrawn again. Um, this is the demo with the sprites. As you can see, the sprites are moving over the background, which is continuously scrolling as usual, as in the previous examples. And now we are starting to see that it's starting to get quite slower. Now the frames per second is 13, which coming down from the 17 or 18 of the previous example. So this means that if we want to have sprites and scrolling backgrounds, we need to optimize. So this is what we are going to do in the next examples. Now, with the optimizations, we are going to start first by trying to not invalidate and redraw the whole scrolling area, but just to invalidate by column ranges. Um, the tiles that are being drawn are just we are just invalidating the ranges of cells that those tiles cover on each column. So on the left, for example, on the top left, you can see there's a tile that covers two columns. So we have defined two ranges for that tile, one on each column. And on the next column, near the bottom, you can see there are two tiles on the same columns. So we have defined two ranges again, but the ranges are covering both of the tiles and everything in between. This is done for efficiency reasons so that we don't need to handle a list for each of the columns, but just a minimum and maximum value, and hope that if we don't have many tiles on each column, we can just have these ranges are are varying slowly. And also you can see some other examples in the columns on the right. As you can see, there is much less invalidation going on with this optimization, and this can be, in fact, can be seen in the demo, which we are going to see right now. As you can see, and comparing with the previous example, the sprites are again going all over the background. The background is scrolling quite smoothly, and we have again gone to the 17, 18 frame per second counter. So this is quite a good optimization. But we can see that it depends on the complexity of the background. This is a simple background. If the background is more complex or has more tiles, the frame rate would suffer a bit since we would be slowly moving into the almost fully invalidating case. Um, I mean, if there are more tiles, the ranges will be greater, and we could be in a degenerate case of the full column invalidation as before. So we need to explore something else in the next example. So the next test is test number 4, which is called SP1 partial invalidation algorithm number 2. And instead of optimizing the ranges of the cells that are going to be invalidated by each of the tiles on each of the columns, with this optimization, we are going to track each and every one of the tiles that are going to be scrolled. This is exhaustive, so we are going to guarantee that the number of invalidations is the minimum one that needs to be done. Uh, and for this, instead of we need a global list of the tiles with their positions. Also, we need to adjust the positions of the tiles or the bounding rectangles periodically. We also need to add and remove dynamically from the list, because the new tiles are entering from the top and are entering the list from the top, and they are leaving the list by the bottom. And they are also stored left to right. But this has a good point, is that the tiles are sorted by y coordinate. I mean, they are sorted vertically, so it makes it easy to add and remove from the global list, because the list is managed, or can be managed in a FIFO order. So we can use a ring buffer for efficiency, and just adding tiles at the end and removing tiles from the head, and using it as a rolling buffer. We need to define the maximum number of tabs that will be on screen at any time. So this is also good, because we can control exactly how complex the background is, and we can tune it as we need. And well, and all this can be done at compile time. So this seems a good optimization. So let's see it in action. We can see it here. Again, it is a smooth movement. It's showing now 18, 19, somehow, sometimes it climbs to 20, we can see. Um, so this is a good optimization. I think this is as good as we can get, because we already know everything regarding all the tiles that are moving on the screen, and that's it. So on with the next tests. The last test that I have done is some playing with scrolling, and by doing some parallax scrolling, which is an interesting thing. It's mainly aesthetic, because I mean, the game normally takes place in a central scroll area, which is not a parallax, but it is nice to see. So it would be interesting to see how it impacts performance, um, when it is added. I needed to reorganize the code a bit, because now we have to handle not one scrolling area, but three different scrolling areas with three different speeds, and different criteria for adding new tiles at the top. The code had to be generalized and refactored, but I did it. Now you can see the zones. The zone number one is the central zone, which is analogous to the ones that we have been seeing in previous examples. And the scrolling zones number 2 and number 3 are the parallax zones that are scrolling a bit faster than the central one. The central one is scrolling at 1 pixel per cycle, and the other ones are scrolling at 2 pixels per cycle for zone number 2, and 4 pixels per cycle in zone number 3. So the external ones are faster than the internal one. I have found that this has a big impact on performance. So it would be interesting if we want to use parallax or not, depending on the game or the gameplay, or if we want it to be pretty but a bit slower. We can see here it in action, and we can see the parallax effect. Um, I'm sorry about the tiles, because I'm not a good artist, so they are not very pretty. But you can see the effect of the sides scrolling faster, and then the medium area scrolling a bit slower, and the central one, which is where the action happens, scrolling at 1 pixel per cycle as usual. Sprites are all over the place as in previous examples. We can see here that the frame rate has dropped quite a bit. Now we are having around 11 frames per second, which is quite a bit lower than previous examples. So as I said, this needs to be evaluated if we want this effect or not. So after having seen all these examples, I drew my conclusions. The first and most interesting is that scroller games with SP1 are a real possibility. It's not something that should be discarded. It is very convenient to use SP1 and to handle our background, our scrolling background and sprite layer. Um, as usual, we have to trade performance for convenience, but this is normal work when we are developing. I have also found that the SP1 update is the critical part regarding to speed. So optimizing anything which interacts with it really pays back, as we have seen in the optimizations in examples 3 and 4. And I have also found that the partial invalidation number 2, which is tracking all background trials, is the most efficient and the fastest of the algorithm, which is to be expected because we are just tracking everything. And I have found that parallax is nice, but it comes with a big performance hit. So you are the choice is yours with this one. Also, finally, after doing all these examples, I switched all the examples to work on a 16 by 24 screen area. I redid all the tests. I found them to be a bit slower. It was to be expected, but the numbers are still very reasonable, as can be seen in the tables that we have seen in the forums, in the performance tables. Uh, so um, so that's it. These are the conclusions. And then, as for the next steps, I said in the forums that I wouldn't be exploring any more SP1 scrolling, but I have had some new ideas. I have done some preliminary SP1 horizontal scroll tests, and they are showing promising results. So I think I explored that also. And after that, the most interesting thing that I have thought is to mix both of them. I have some ideas for multi-directional scrolling, horizontal and vertical at the same time. This would allow to develop some quite interesting games um, if it shows that it can be done. I suppose the scrolling window will have to be reduced mm, a bit at least. But anyway, I think the scrolling multi-directional scrolling games are so pretty that it may be worth to it may be interesting to do it. And also there is a possible integration of this with my Rage 1 engine, which is an adventure engine, as I said. And this is currently screen switching based. I mean, when you just go to a new screen, it gets deleted and a new screen is fully drawn. But it could be adapted to work with a scrolling map if we can do it uh, with us, with the tests. So that's it. That's it for me. I have these are my tests. Everyone is welcome to check the code and to add anything and to comment anything in the forums in the set88dk or the Spectrum Computing forums where I have published the articles. And finally, I have some greetings that I'd like to send. First, I would like to thank Dominic and Derek from the Set88 DK forum. Also, of course, I want to thank Alvin Albrecht for SP1. This I wouldn't have been programming the Spectrum without SP1. And also very special thanks go to Javi from the Set88DK Telegram group. You encouraged me quite a bit to continue with this. And finally, thanks to all of the Set88DK and Spectrum Consulting Computing forums for your moral support. Thanks a lot, and see you on my next video.